Good afternoon, everyone. So up till now, we have seen the headers of UDP and TCP. So if you remember, we have seen this header format, and these are the flags that you should be set while sending the messages. So I'll quickly uh, review these 6 flags. Fin flag is set for the last packet in TCP protocol. If it is 0, then that means there are more packets to come or to arrive. SYN flag is always set for the first packet in the communication. Reset flag, in case of there is any problem, we reset the complete communication. We restart the complete communication. But this is 0 for all the normal messages. Push flag, if you want to push the current packet into the buffer straight away, so that is for that push flag is set to 1. Then acknowledgement flag will be used only in case of you are acknowledging any message. And then there is a urgent flag. If some data from this packet is very urgent data, then you have to mention the address of that urgent data. So these are the flags that you have to use while sending the messages. We have also seen this simple case where you are establishing the connection, what are the sequence numbers, what are the acknowledgement numbers, and all these things. So this is a simple example. Let us consider that this is the first packet, hello packet. You are sending it to the receiver. Okay. For example, sequence number is 8000. Now, why 8000? There is no answer why 8000, but just hypothetical number we are considering. It can be 733 or 01 or any number for that matter. So hypothetical number we are considering here. Why S flag is shown here is we are setting the sync flag, because if it is set to 1, that means it is the first packet in the communication. So that's why we are setting up the sync flag. As soon as you send this packet, it will be received by the receiver or server. I hope I'm audible. Am I audible?
Yes.
Thank you. So as soon as the server receives this packet, server sends an acknowledgement, okay, as a reply. Now acknowledgement will have a 1 number ahead, 8001, okay. But for the sequence number for this packet will be different, because this is processed by the operating system which is available here. Okay, this operating system is completely different. That's why that operating system has created this sequence number. But as soon as it received in the server operating system creates a new packet. Okay, this is a new packet. For that, sequence number has to be provided. And what acknowledgement? This is the acknowledgement. So you are just incrementing it by 1 to the previous sequence number. And now, as this is a acknowledgement, you are setting up the acknowledgement flag as well. Now this is also set, sync flag also is set, because this is also first packet from server to client or from the receiver to the sender. So that's why SYN plus acknowledgement flag, both are set in this case. Okay. And then this is the three-way handshaking. You are sending acknowledgement to the acknowledgement. And that's why you are not setting the SYN flag here in this, because this is the now in the communication second or third packet in the communication. So we are not setting the SYN flag one, but this is an acknowledgement to acknowledgement. So you are setting the acknowledgement flag one. Now you are acknowledging which message? 15,000 message. Okay, so that's why you are incrementing that, and the sequence number is 8001 because this is the next message in the communication. So this is how the three-way handshaking happens along with the acknowledgement flag and SYN flag. Okay, so these are the message communications in three-way handshaking. Now this is a new concept, TCP transmission policy. What happens is we already have studied sliding window protocol, TCP, but here there is a slight modification which says TCP sliding window protocol. The concept is very same. What happens here is you have a sender has some buffer of 4 kilobytes. Okay, and receiver also has the buffer of 4 kilobytes. What happens is at this moment receiver's buffer is empty. As soon as you are sending the data from the sender to receiver, let's say you are sending 2 KB packet, okay, with as this is a sequence number 0, that means it is a first packet in the communication. So you are sending 2 KB of data and sequence number 0. As soon as it is received here, obviously that 2 KB of data will get stored in the buffer, okay, and this 2 KB is empty. So what receiver will do, receiver will send the acknowledgement of what empty size of the buffer is. Okay, window used is 20 KB, that is 2 KB, and acknowledging the empty size. Okay, so that is one thing that you have to remember here, what you are acknowledging. Okay, so once you receive the acknowledgement from the receiver, a sender will come to know that it can only send 2 KB of data. Okay, it sends the 2 KB of data. Okay, when the receiver buffer is full, it sends a window size of 0 and acknowledging all 4 kilobytes of data. Okay, it has received both the packets and you are acknowledging all 4 kilobytes of data. But now you are sending as window size 0. Window is not empty. So that means what? You have to wait until there is a buffer empty. So what happens is when the buffer is full, your application, let's say WhatsApp application or any web server application, Apache web server or any FTP server, what it does is it keeps reading the buffer. Okay, let's say it reads the first 2 kilobytes of data. As soon as it reads the data, this data will be removed from the buffer, and obviously the packet will be created which says that what is the window size available. So 2 KB of window size is available right now, and this message is sent to the sender, and after that sender can send the further data. Let's say you have only 1 KB of data remaining. Okay, total 5 KB of data you want to send. So in that case, you send only 1 KB of data, which gets stored in the buffer. And next time you acknowledge with the window size of 1 KB, because right now window is just 1 KB of empty space in the buffer. So this is how this empty window keeps moving from here and there, and this is called as sliding window protocol. Okay, and this is how TCP works with the sliding window protocol? If there are any questions, we can discuss. And what happens at the, let's say this is the buffer. Okay, application is running on the server or receiver's end. How does the application works? Let's say whenever the receiver's buffer is full, what happens is application has an access to the buffer, okay, and it keeps reading some data, okay, from the buffer. It is not fixed that all the buffer is read at the time. It keeps reading the buffer depending on the header packet. Let's say header packet says that it has some urgent data, or it has some push flag 1. So in that case, what happens is application has to have access to this buffer, and as soon as the urgent data is there, or some data has to be pushed to the application, it keeps reading the multiple size of the data, variable size of the data. And once the size is data is read, that window is available. Okay, so you have to update the segment, window update segment in the sliding window protocol. And as soon as the window is available, the receiver sends the data, further data to the receiver. Sender sends the further data to the receiver, and buffer always gets full. So this kind of scenario is called a silly window syndrome. Okay, so solution to silly window syndrome is what? Is to read the complete buffer at a time as far as possible, so that the window size which is available should be of maximum of buffer. Okay, it should not happen that if application is reading 1 byte, then this sender will send 1 byte. So this will increase the overhead on the sender and receiver. What should happen is the application should read more into the buffer. It should not read 1 byte at a time, or very slowly. So this kind of scenario is called as silly window syndrome. And solution to this silly window syndrome is to read a maximum amount of data from the buffer. Okay. Now that can be decided by the application and operating system depending on their constraints. Okay. So this is another topic that is real-time transport protocol. It is also called as RTP. So we have seen up till now UDP and TCP. There are few more protocols in the transport layer, which is called as SCTP and RTP. So we'll study only RTP. SCTP is a combination of UDP and TCP. But RTP is a protocol where you have to send a real-time data. That is very important. RTP is always used in the live streaming. So if you can, if you just compare this with the, let's say there is a live cricket match or any live program which is getting recorded, it has to be broadcasted on, let's say, most of the channels. What happens is you have to use a real-time protocol where actual live data is transmitted, and at the receiver end you get the recording without any delay. So this is a very difficult thing to achieve, but using RTP it is achieved almost without a delay. Why I'm saying almost without a delay? There are plenty of parameters which gets added, and you actually don't get the live streaming. Real time is very difficult to achieve. but there is with some very less delay, the live streamings are broadcasted. So what happens is, obviously it has to be a multimedia application, because RTP is used by most of the multimedia application. For example, news channels, uh, broadcasting, cricket, all broadcasting channels and all these things. So multimedia applications are the ones who are using real-time transport protocol. And then you have a RTP. You have to use UDP. Now here is the reason why you have to use UDP along with the RTP. What happens in RTP is, I'm sorry, TCP is, let me just go back. What you have to do is you have to ask the other host, are you ready? Then host replies, yes, I am ready, we can communicate. And then host again sends the acknowledgement, okay, let's communicate, let's talk. So what happens here is you are spending some time before you start communicating. So this will add more delay into the communication. What happens is there is a surety that the other end is there to receive your data. So there is a confirmation of data can be uh, reached at any moment of time. So TCP gives you the reliability of data can be re received by the receiver because he has agreed for the communication. But it is introducing some delay. Okay, it takes some time to get delivered. Whereas what UDP does is UDP doesn't go for any request or any acknowledgement. UDP immediately sends the data to the receiver. Now it's receiver's job for it's receiver jobs to receive the data and do whatever he wants to do. So that's why UDP is faster than TCP, and that's why if you want to use RTP, real-time transport protocol, you have to use it with the UDP itself. Okay, and then you have Internet Protocol, Ethernet Protocol, and so on. So this is the protocol stack for RTP, and this is a segment, protocol segment. Right, starting from physical layer, you have a Ethernet header, then you have a network layer, that is IP header. Then you have a UDP header because you have to use UDP, and then you can use RTP. Okay, where your live streaming data is there, which is called as RTP payload. Now it can be images, it can be a video, it can be any multimedia files. Okay, and this is what the packet structure for RTP is. Now RTP protocol header is like this. You have a version, you have priority, what kind of portion of the data is prioritized. Then you have CC, that is contributing chair. That means what? Let's say there is a live match going on. It can be either football match or cricket match. There is no only one server who is contributing the complete recording. What happens is there are multiple servers who are taking or who are participating in the live streaming. So what happens is you have to give the number of those contributing communication servers here in the packet. Then what kind of medium you are using, what is the payload type, is it the image, is it the video, or is it the live streaming, what kind of payload type you are having, then the sequence number, timestamp number. And then what you can say, synchronization source identifier. Now let's say there are 10 uh, 10 such servers, okay, who are contributing live match, but this packet belongs to which server of those out of 10? So currently, what is the server identifier from which the data is being broadcasted? So that identifier has to be given here. Uh, Again, in the contributing source identifier, what happens is, let's say current server is contributing to the live streaming out of 10. Let's say the fourth server is contributing, that identifier is there. But in that fourth server, there are multiple uh, stages where the video is getting transmitted. Not only one channel, through multiple channels, it is getting broadcasted. Now, let's say for some broadcasting, it is paid, and some broadcasting, it is free. So for free channels, what they do is they add 5 minutes delay. So you must be knowing this. For paid channels, you get actual live streaming, but for free channels, you get some delay. Maybe 1 minute delay, 5 minute delay, or 10 minutes delay. It can be anything. So you have to be synchronizing all those sources for particular broadcasting. So what kind of synchronization identifiers and contributing source identifiers are used? That message or that information has to be provided in the packet header. Okay, so this is what the RTP header is. Then TCP also works on congestion control. We have seen congestion control algorithms in network layer, in the physical layer also, data link layer. And congestion control also happens in the TCP also. Not TCP, the transport layer. So, and the similar algorithms are used. This is a leaky bucket algorithm that we have seen. What happens is input flow is high and the output flow is small, because this bucket cannot contain all the water that you are forcing in. Or it can happen as the source is very slow, but the output is very high. Output speed is very high, needs very high. So there are multiple situations where you have to control the flow, okay? And it can be controlled with the leaky bucket algorithm. We have seen leaky bucket algorithm where there is a small hole leak in the bucket, and that the size of the hole in the bucket has to be decided using what kind of bandwidth you are using, what kind of link you have, and all these things. Let us say the input is of 12 Mbps line, and the receiver is of 2 Mbps line. Sometimes you send 12 Mbps speed, sometimes you send 2 Mbps speed. So what you do is you channelize the speed to 3 Mbps, so that there will not be any variation. Even there is a burst of data, it has to be managed with a fixed data rate. Okay, and that can be managed with the leaky bucket algorithm. So actually, we have studied this. I'll not spend much time on this. The token bucket algorithm, what happens is there's a bucket of tokens. Whatever the data, whatever the packets are coming from the source, what you have to do is you uh, pick up the token, and then move into the network. As soon as you move into the network or the operating system, processor manages this packet along with the token. Okay, and once the packet is sent out of the network, then you bring that token back to the bucket. And this is how, let's say, if there are no tokens in the bucket, what you have to do is you have to wait until there are tokens in the bucket coming into the bucket. So this way you are controlling the flow of the packets, packet flow control uh, with the token bucket algorithm. So this is a very simple algorithm of controlling the flow and how to control the congestion. Then quality of service is one of the jobs of transmission layer, transport layer, and quality of service depends on these parameters. I suggest you to go through these parameters one by yourself, study yourself. Throughput, what is the transit delay? Throughput is a, if you remember, we have seen the slotted aloha throughput, pure aloha throughput. The values will be where we have seen as 0.18 efficiency and 0.36 efficiency for pure aloha, slotted aloha. So the throughput of the any network, that means how many packets are getting transmitted per second. So that will be a throughput. Transit per delay. What is the delay in the transmission? How much residual error is there? What kind of protection you have? Do your protocol supports the priority and all these things? So quality of service depends on these parameters. And these are some of the questions that you can answer for yourself. You can study these questions and find out these answers. If you have any doubt, this is the end of the unit 3. We'll quickly start unit 4, which contains all the applications where DHCP protocol will be studied. Then FTP will be studied. Then what else? There are plenty of protocols. There are at least 12 to 14 protocols studied during unit 4, and if you have seen the active learning mail, most of the protocols are studied from the application layer itself. So let me just stop sharing and open the So these are the protocols that you are going to study in this unit. DNS, FTP, SMTP, Telnet. All these are the protocols. We'll study them one by one. And remember, these are the port numbers, which are the fixed port numbers. If you remember, we have seen system port numbers and user port numbers. So these are the actual system port numbers. Some of the port numbers are for TCP, some of the port numbers are for UDP, and some of the protocols uses both the TCP and UDP. As you remember, if you have noticed, this is a network layer. Network layer uses IP protocol, internet layer protocol. Then comes the transport layer protocol, which uses two protocols, TCP and UDP. Okay. And at the application layer, which protocols are used? This is the list of protocols, but all these protocols have uses TCP. All these protocols uses UDP. Some of the protocols uses both. DNS uses both. Okay. DHCP uses only UDP. It is not used with the TCP. So there are some reasons behind it. We'll study those reasons one by one, okay, as we move on. So first we'll study DHCP. As you know, we have seen DHCP is a dynamic host configuration protocol. What it does is it automatically assigns the IP address to a machine. Previously, before DHCP, there was a bootp protocol, okay, bootstrap protocol, which boots the machine and finds out the IP address, its own IP address. I'll give you the situation here. As for example, we have purchased, let's say, 100 machines for our startup. We are starting a new company. What you have to do is, let's say there is no operating system installed on these machines. So what you do is you connect those machines in a LAN and power them on. But as they don't have any operating system, you cannot use them properly. But does it mean that they will not have any IP address? The answer is yes. They can get the IP address without any operating system. If you notice, or if you know, nowadays by default, at least there is a DOS operating system which is installed just to access the basic drives of the machines. So what happens is bootp protocol gets executed immediately, and what happens is bootp there is a bootp server who is allotting the IP addresses to the machines. But the problem, there was some few problems of bootp. It was manual mapping and all these things. There were many problems. So that's why DHCP was introduced to to overcome with all the problems that bootp has. Basically, bootp and DHCP does the same thing. Okay, we are studying right now bootp, but it is the modification of DHCP is the modification of bootp. So basically, bootp uses only manual mapping. Okay, DHCP, on the other hand, it has three ways how IP address assignment can be done. One is automatic, the other one is dynamic, and the third one is manual. Automatic is whenever you want some IP address as a permanent, okay, permanent assignment. So if you have noticed, whenever the machine comes into contact with the DHCP server, immediately next available address will be given to that machine. But what if I as an administrator want my machine to get a particular IP address as a DHCP, then I will need an automatic IP address assignment, okay, which is a permanent for myself, which will not be used to anyone else. Okay, dynamic, it is exactly opposite thing. Any IP address, unused IP address, can be assigned to any number of, which is fair number of machines in the network. So that is the dynamic. And manual is very simple. You configure these IP addresses just like bootp does. These are the parameters which gets assigned from DHCP server. Now these parameters were not discussed with you earlier. If you remember, DHCP server was giving the IP address. You have configured DHCP server with the IP address pool and all these things. But along with the IP address, there are some more parameters like what is the DNS server, what is your subnet mask, what is the default TTL value. TTL is time to live. MTU is what is the maximum transfer unit, what is the maximum data that you can send at a time. So these are the values which you automatically get from the DHCP server. Now what happens is, once these values are offered to you, let's say I'm the DHCP server and you all are requesting for the automatic IP address from me. So you get connected with me and I'll be assigning the IP address to each one of you. So PH1, PH2, PH3, and so on. So I'm assigning the IP addresses to you. Now what happens is, I also will offer these values, say DNS server. So let's say you have to contact Neha ma'am for your confirmation, some other confirmation. What is the subnet mask? This is what is your subnet mask. At a time, only you can transfer 50 MB of data. Okay, this is what I am proposing to you. What happens is, it is your job now to either accept these values or reject these values. If you accept the values, then you will get the IP address assignment. If you reject these values, I will not assign any IP address to you as a DHCP server. So it depends on the client and server, what kind of values are accepted and what is the IP address assignment. So what we'll do is, we'll see one example. Okay, so this is a DHCP header, protocol header. It's a very simple thing. Don't get afraid of what is there on the slide. I'll quickly tell you what is there in the header. Hardware type, what is the operation, whether you are operation code. OP is the operation code, whether you are requesting or responding. That means request is there for if client is sending the message. If server is there, then it's a response, so server is sending the message. What kind of operation is there? What is the hardware type, whether you are using a network or Ethernet? What is the length of the hardware? Is it a 46-bit MAC address, or is it a flat addressing? So all these things are there. Then number of hops. It is set to 0 by client. Okay. And if this server is in the same network, then it is set to 1 in the same network. For example, I'm sitting in the city Pune, and I'm working in a company called as XYZ. My XYZ headquarter is at Delhi. Okay, and the DHCP server is also at Delhi, but obviously it is not in the same network. So sitting in Pune, if I'm getting the IP address from the Delhi server, the hops cannot be 1 because we are not in the same network. So we are connected. Pune city machines and Delhi city machines are connected with each other using many different networks. So those many hops has to be mentioned over here. Then you have a transaction ID. It is simple identifier. It is the time that has elapsed from the client has started. Let's say I have asked you to join my lecture. Not everyone joins at the same time, right? So what happens is, I ask you to join at 2:30, but let's say there is a waiting time, waiting window, or what you call it as waiting room activated. If everyone is getting into waiting room, and I can't keep checking a waiting room in every 1 second. What I'll do is, I'll keep checking the waiting room after, let's say, 5 minutes. Then I come to know that which client or which of one of you has joined at what time, since what time you have joined. So that period is mentioned over here, seconds. Okay. And then you have what is the client's IP address, what is the your IP address, and so on. So these addresses will study in the example. Okay, so don't worry about these addresses. These are the number of messages that gets transmitted whenever DHCP you are connected to DHCP server. Uh, let's say first message is DHCP discover. Okay. Uh, Obviously, when all of you join in the network, you don't know who is the teacher, for example, who is going to teach you. So what happens is a client, when joins the network, it discovers the DHCP server. Like it sends a message, DHCP discover, that who is the teacher, who is the server. And this is just that message. DHCP offer is a response from the DHCP server. So teacher will give the offer to all the student that I'm your teacher, I'll teach you. So with some parameters, those parameters are these parameters. Okay. Now, if you accept those parameters, then you give the positive acknowledgement, DHCP positive acknowledgement. If you reject those parameters, if you don't like my name, if you don't like my face, then you give a negative acknowledgement to me so that I'll not teach you. So these are the messages which are very simple messages. We will study these messages one by one with an example. Now, let's say client is joining the network. There is a DHCP server available in the network who can offer the IP address. So the first message, whenever client gets switched on, what happens is client sends the DHCP request. I'm sorry, DHCP discover in the network. Now this is a broadcast message, and only server can respond to this message. Okay, server responds to the message with some DHCP offer. Okay, that I'm the server here. If you would like to work with me, you can send me the next message. The next message is DHCP request. What is this request? It is requesting an IP address. What kind of service I'm providing you? That is IP release. So once I receive the request, server is sending the acknowledgement that I can give you this IP address. Okay, and so on. So these are the types of messages which are sent in some sequence. So if you have noticed, this is the first message in the list. This is the second message in the list. Request has to be third message, fourth message, and so on. Okay, so DHCP decline and DHCP acknowledgement can be kept at same level. Okay, either fourth or fifth, and so on. So now, if you remember, there are some values that I have skipped in this header. Okay, client's IP address, your IP address, server IP address, router's IP address. Okay, so I'll tell you the values of those now. Destination IP address. Okay, MAC address, destination's MAC address, source IP address, source MAC address. Okay. Now, whenever the client comes as a newbie in the network, it doesn't know who is the server. Server's IP address, it is not aware of server's IP address. So what it does is it broadcasts the message. This is a DHCP discover message. Okay. It will put, because it doesn't know its own IP address, so it uses 000. Okay, but it knows its own MAC address, so it puts the this own MAC address as a source MAC address here. Then server response here, what it does, it doesn't specify destination IP address. First of all, it only specifies the destination MAC address. It picks up the MAC address and put it as a destination MAC address here, so that the packet will be received by this client only. Again, it will not provide any IP address here because the IP address assignment is not done yet. The source IP address, source server's IP address is mentioned over here because server knows what IP address is there. Okay, and this is the server's MAC address. It is an offer message, DHCP offer. This is a DHCP server, this is a DHCP offer. Now, server is offering something to client, okay, with some parameters. Now, it sends the IP address, okay, as a your IP address. Okay, this is an offer. Now, let's say I am the DHCP server and I am offering PH1 IP address to whoever joins first. So I'm just offering you your IP address. It doesn't mean that your IP address is this one. It's not like that. I'm offering you this IP address. If you accept it, your IP address will be fixed. Okay, so that way, if client responds as a request, okay, requesting an IP address for assigning, then what happens is, again, it doesn't have any IP address assignment, so it uses destination IP address as 255.255, but it only sends a request. Okay, again, source IP address is 0. It mentions the source MAC address as this one. Okay, now this request is accepting all the parameters which are mentioned in the offer. As soon as you send a request, it is a positive acknowledgement, okay, with a destination IP address as this one. Now, what is this? 10.1.10.100. It must be the value kept in the your IP address. Okay, so in your IP address field, this IP address was mentioned, which was accepted by the client. Okay, and if you have noticed, all the addresses are mentioned in the last message here. Okay, the destination MAC address, IP address, MAC address, source IP address, and so on. So this is how a IP address assignment is done using DHCP. Okay, if you have any questions, we can discuss or we can stop. Okay, in last online lecture, I have noticed that there were only 30 odd students attended the lecture. There are 60 responses I have received. I don't know what you people are doing. There are only around 57, 59 students in the class, but I'm receiving 60 responses. I'm considering all the attendances which are marked in 10 minutes of the lecture, finishing of the lecture.